In this video, we're going to discuss linking sugars. So, when we think of sugars, we start with Fischer drawings. Those are open, single sugars. That is actually a very rare form to find a sugar in. The vast majority of times in biology, your sugar is actually a ring, and most of the time it's not a single ring. Rings will connect to one another. And so here we have an example of alpha D-glucose in its ring form. You know it's in its ring form from the name because it has the alpha. If it was just D-glucose, it could be the straight chain, but to be alpha means you must be in a ring form. Same with beta. If you're alpha or beta, you must be in the ring form because that describes the anomeric carbon. What can happen is if I had a second alpha D-glucose, well, what I really have going on right here at the anomeric carbon, that is a hemiacetal. So if we think about our hemiacetals, how did we know what a hemiacetal was? Well, if you have a carbon, and that carbon has an OH and is part of an ether, that was our way of identifying that it was a hemiacetal, or a hemiketal, depending on if there's a hydrogen or a second R group on that carbon. One of the reactions with hemiacetals was that if you add another alcohol, well, it can attack that carbon and push out the OH. The result of this is that you have your carbon, a hydrogen, the original ether-looking bit, and now a second ether-looking bit, as well as a water. What you have now is a carbon that has two ethers that share it. This was our full acetal. Well, I have a hemiacetal sitting at the anomeric carbon, and I have nearby alcohol groups on other sugars. They can interact. What will actually happen is that this alcohol will attack the hemiacetal and push out that OH. The result of this is, well, the OH leaves, the other hydrogen leaves, and the two sugars become linked through that oxygen. That oxygen is now connected to the fourth atom, the fourth carbon of one sugar, and the first carbon of another sugar. We have created a link that bridges two different ring structures together by turning that anomeric carbon of the left sugar ring into a full acetal. To do this, we have to describe the connection. And so we say that this is an alpha 1-4 linkage. It took the alpha direction on carbon 1 of the first sugar, and it connected to carbon 4 of the second sugar. The oxygen will always be in the same direction for both of them. It was down originally for carbon 4. It's still down on carbon 4. It was down originally on carbon 1. It is still down on carbon 1. When you connect sugars like this, you can keep doing it. There's another front anomeric carbon right here. There's no reason you couldn't do this again. If I had another glucose unit, these two could interact. You could lose water off one, and then have these two rings pull up and interact. So make that oxygen a little bigger, just so you can see it clearly. You can chain these more than once. If you just have 2 rings together, it is a disaccharide. If you have 3 in a row, they are trisaccharides or oligosaccharides. And if you, generically draw it here, do this many, 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 many times, so sugar, oxygen link, sugar, if you were to do many, 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 many of these, you have polysaccharides. You can link sugars into enormous structures. If you have 1,000 to 2,000 units that are of alpha D-glucose in alpha 1,4 linkages, there's actually a name for this. This is amylose. Amylose is starch. That's what you think of when you think of starches. So a potato, most of the energy stored in a potato, is amylose. It's actually just really long chains of these alpha D-glucose 1,4 connected units. They don't actually make perfectly straight lines. Amylose spirals on itself as it goes. And so you have lots of sugars along it, but they kind of twist a little bit as they go along. And so you get these larger structures formed from the connections of many, many individual small sugars. This is actually why you can test for starch with iodine. Not everybody knows that, but if you take purple iodine and you put it to starch, the iodine fits inside these curls and turns blue. And so it's one that tests for starches and things, so they can just add iodine to it. This is primarily an energy storage mechanism. It is you build a bunch of sugars during the day or over the months, you grow your little bulb on the ground for a potato, and then it can be used to grow the plant later as an energy storage. Well, this is great if you do alpha D-glucose, but what if you do beta D-glucose? Well, we still have our glucose. Only difference this time is that the anomeric OH goes up. All the other OHs are in the same position. If you do a beta 1 to 4 for D-glucose, well, our second monosaccharide is going to look the same, but carbon 1 on the ring and carbon 4 on the ring, we're going to connect them. That alcohol is going to attack the anomeric carbon, push out the other OH. The result of that will be the other OH leaves, this hydrogen will go join it, and our sugar, well, we were up at 1, we still have to be up at 1, and we were down at 4, we still have to be down at 4. So they'll connect like this. It's a little more stair step instead of our straight that we saw with the alpha. And this is true, this will continue. If you did a bunch of beta 1,4s, you end up with a much more stair step structure. This is cellulose. Cellulose has a neat property where adjacent groups actually line up really well. Cellulose doesn't curl, it makes these straighter chains, and the OH groups on either side are good at lining up with each other. This makes for strong intermolecular attractions. Your cellulose lines up into long, straight pillars that interact really well and don't move. Cellulose is the structural material for plants. It is what gives them their rigidity. The only difference between that and a potato starch is whether we were alpha or beta when we made this connection. You can break down alpha glucose connections, no problem. But if you tried to eat wood pulp, nothing would happen. It's still made out of glucose, but because of that direction difference, the molecules in our body that would break them down can't. We do not have the ability to digest cellulose. In fact, most life doesn't. A few fungus and a few bacteria are really it. And so any animal that eats plants, like cows that eat grass and things, that primarily just eat the roughage, they actually have fermenting stomachs. There's a bunch of bacteria in there that break down the cellulose, steal some of it for themselves, but the other free sugars that got created are then digested by the cow. And that's the only difference. A potato and a chunk of wood are made of exactly the same molecule. They are made of D-glucose. The only difference is in the direction that we attached them. So alpha and beta is critically important, and seeing how they connect between ring sugars, the terms so we know what connection we are doing, is also very important. So being able to say that it is beta 1,4 versus alpha 1,4 lets us know which of these structures we're creating. Side note, cellulose, if it is wrapped in lignin, this is where really big structures like trees came from, the hardwood. Plenty of plants have cellulose, but they don't get too big before they can snap, but lignin helps bind them together. When this first evolved, nothing could digest it. These days, some fungus and some bacteria can, but originally nothing could. And so the first trees never decayed. The scale tree, when developed this, could grow 100-some feet tall very quickly and would rise well above all the other plants to steal the sunlight. But they hadn't had time to evolve roots, so windstorms would just knock them over. They fell, they broke, but nothing broke them down. They didn't decay. And so more and more scale trees just piled up and piled up over time, pressing down and pressing down. And the massive amount of them compressing for so long drained a huge amount of carbon out of the atmosphere. It's actually caused an ice age eventually, but it also produced all the coal. Almost the entirety of the coal on the planet is actually from the Carboniferous period when these trees first started growing. For several million years, there was nothing that broke them down. So any of them that ever grew, that carbon stayed forever removed from the atmosphere. They compressed, they got buried over by silt and mud flows and flooding over time and just squished more and more, and that is where all the coal mines in the world presently come from. All of that because of a directional difference with D-glucose. You can have other connections. They don't have to be 1,4s. Let's look at this one real quick. Let's go back to our amylose. Well, that glucose ring that is connected to my next glucose ring there's a lot of other alcohols. And you can have another glucose that pulls up near a different OH. If you have a alpha 1,6 connection, effectively what happens is you just make another ring come off the top of one of your already existing rings in the chain. This is a branch, and you can do this all over the place. You can have other branches. Instead of one single long chain, you can have branching amylose. This is amylopectin. Why you do this? It's a little bit different type of storage. A single chain, well, we access the sugars at the end of a chain. The enzymes that break them off snap on the end and start cutting. And so it'll cut one and remove it, and then it will cut the next and remove it. If you have only one chain, you can only cut one at a time. But if you have a branched chain, so I'm going to simplify the drawings. We got a lot of sugar units, and there's a branching with more sugar units. And these even have their own branches. Versus a single chain. Well, I can only break one off at a time if I have a single chain, but if I have multiple, then each of those ends is available. The speed at which you can free up sugar, and therefore free up energy, is greater from amylopectin than it is from amylose. So long-term, easy, slow storage, amylose is better. But for anything where you'd need fast access, amylopectin becomes better. Additionally, it has neat properties. Pectin, if you've ever made jam or jello, pectin can be used to spread out. It makes these kind of meshes on a molecular scale that can get stuck together. And so if you dissolve them in water, they fan out, they overlap with each other, and then they can get caught on one another. They make a net. And so if you've ever mixed jello, it's a little bit of powder and a lot of water, and then suddenly it turns solid. The sugars are attracted to the water, the sugars get caught on each other, and then they can't move, and everything just stays stuck together. So a couple neat uses for branching systems of amylose. But you can branch it even more. Most amylopectin tends to be 24 to 30 units between branches. So they're reasonably spread out. You can get much more branching, where you have branching just constantly. This means you have ready access to even faster release of energy. Glycogen is the branching amylose version in animals. Animals need to move. Plants don't really need to move, but animals do. And if you suddenly need a bunch of sugar so you can be running, you need to free it up really quickly. If your muscles need to lift things, they need the energy. Glycogen is mixed all around so that it's a quick access source to an enormous amount of energy very quickly. Glycogen tends to be 8 to 12 units between branches. And so there are far more branches and therefore far more access to the energy in glycogen. And so we tend to find that in animals that move, where plants don't really need it, and so we don't see it as often. So this is an example of, again, just linked sets of alpha-D-glucose. They can come in large varieties, how you connect them, whether it's all just alpha-1,4 or you throw in some alpha-1,6 to create branches, lead to all the varied properties we can see in these molecules. Sugars can be enormously complex, as we will continue to see, but the root component of them is still the same. I have my sugar, and it is one pyranose or furanose ring, and then that can connect to another pyranose or furanose ring to create larger and larger structures.